Our webinar today, the spiral freezer and cold storage loading dock application. The purpose today is to, number one, review the challenges that we see in these cool or cold applications, the challenges of moisture. Where do they show up? What do they do? And then understand the solutions. We're going to look at several of them. Obviously, we're going to be focusing on the desiccant solution, the CDI desiccant technology, and how to remove moisture. But what's the challenge? Well, as those temperatures drop, that moisture shows up as fog. It shows up as condensation. That's going to degrade the product. That's going to cause issues with packaging. And you see here the fogging of that moisture, that visible moisture now, right through this pallet door. Makes it very difficult to see. And our point is that it's going to decrease worker visibility. It makes it difficult to even see sometimes through that fog, and that can cause issues. But additionally, this condensation, as this one would say, it reduces the shelf life. So we have a challenge in condensation on our product. We have ice buildup throughout this portion of the facility. It's going to even hinder door operation to get in and out of the freezer. That ice buildup is going to increase component failure, as you can see in this photo with the evaporator fan. As the ice builds up on the leading edges of the fan, it can and will become unbalanced. The fan blades will wobble and break potentially, and or the motor bearings. So we're going to increase component failure by that ice buildup. And in this case, look at how that ice will impede the product being conveyed. We're there to make this product, to get it done as quickly and efficiently as possible, and bumping it off the conveyor is not a good idea. Also, ice buildup is going to reduce that efficiency or productivity of our folks working in that facility. So ice buildup is a challenge. It builds up on the piping, it builds up on the ceiling, on the evaporator coils, on the fan guards, and if we can even see it on the strip curtains as they would access into the packaging areas. Ice buildup, obviously, on our evaporators is going to now require frequent defrost. How do we keep that evaporator doing its job? Well, we have to defrost it. So the point is, with ice buildup, with frost on our coils, that's going to increase our utility costs as we put heat back on that coil just after we tried to take the heat out of the room. We've also even seen this, where this particular manufacturer had 2 people all day long just to clean up the room. So obviously that's going to slow down some production. It is also increasing risk of worker injury on those slippery surfaces. And it's not just in the freezer, it could even be at the loading dock where we have those cool surfaces, that moisture coming in, and we can get some very slippery surfaces. And then those slippery surfaces have to be cleaned up, so regular and frequent removal. So what have you tried so far to stop this moisture, to stop water from getting into the cooler or freezer? Well, many cold storage areas are equipped with strip curtains as the only protection against this moisture infiltrating when that door is open. Well, this approach, it does not provide a vapor barrier. Yes, there's a physical barrier, but as you can see in this strip curtain, at every crack and crevice, which there are a lot of, and vertically up and down here and even in the corners, that moisture is still coming in, the ice is still building up, it's still moving in, and it's because we're not providing a vapor barrier. There's already evaporators that are trying to take this moisture out. What is the limitation of mechanical cooling? Well, mechanical cooling, we're going to take air from the space, we're going to circulate it over a cold coil, we're going to cool it to the point of saturation, and as we keep going down to the point of freezing. But let's just start with cooling to the point of condensation. So the air then across the coil is reduces the temperature, it reduces its capacity to hold moisture. That moisture then is going to condense out on the coil fins. The amount of moisture reduction we can do is going to be limited by the practical coil temperature, or freezing, if you will. Once we start freezing the coil, frosting the coil, now we have to get into regular defrost cycles in order to keep things operational. That becomes standard operating procedure. Then sub-freezing areas that utilize that method, now we're going to have to deal with all that buildup of ice on the evaporator, but also walls, floors, and ceiling. Note that the cooling coil, the primary function of the cooling coil is temperature control. That's really what we want that coil to do, is keep the temperature in the space what we want. Let's start and look at a coil in a normal temperature environment, meaning above freezing. Let's say we have a coil that's taking air out of a process room, 75 degrees, 70% relative humidity. That's about 92 grains. That represents a 65-degree dew point. That coil would typically have then a 45-degree solution being moved through the coil, or a 45-degree coil. We could then come out with a 5-degree approach then at 50 degrees. That brings us down to 51 grains, but a 49-degree dew point. As we do that, that moisture then is going to condense out of the coil into the drain pan, and the water is then going to be coming out of the system through the drain pan. But we want it drier. We want to take out more moisture. We want it cooler. What happens? Well, once we get below freezing, this frost and ice buildup, it's going to start on the face of the coil. It's going to start on those leading edges, and sometimes it builds so fast with improper fin spacing that will actually block the coil quite quickly. With some wider fin spacing, like 4 fins per inch or something like that, or even half-inch fin spacing, we can get that frost, that freezing, that ice to go deeper in the coil, fill the coil up further before the coil stops working. But in doing so, then the defrost cycle takes that much longer to get the moisture or get the ice back out of the system. So that obviously we're going to go through fog, visible sources of moisture, and then frost in order to get down to these cooler discharge temperatures. In this scenario we're talking about right now, that freezing starts to occur obviously at 32 degrees. And we're trying to get out of this coil at 25 degrees. So lots of ice buildup. What that looks like on our psychometric chart is if we start up here somewhere at a somewhat higher relative humidity, and now we try to drive that moisture through all the way down to this lower point. Look how we're passing over the 100% relative humidity line. So this zone then, we're going to be creating fog to start with, then frost, and then ice buildup as we would try to get down into these negative temperatures. So ice, 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 we're building up ice all over the place with mechanical cooling. There is a limit to how much moisture then that we can remove by mechanical cooling. The third potential solution for keeping moisture out of your cold storage area are air curtains. A curtain of air, a high velocity airstream across the entire door. Whenever the door is open, this is on. We're moving air down across this opening at 3,000, 4,000 feet per minute. And in doing so, it creates a pressure that resists moisture to a degree, but mostly the air from infiltrating into the air curtain, into the cold storage dock. I'm going to just erase these lines on here for just a second and make one other point for you. In a cold storage area, this air on the other side of the door, we're looking into the cold storage area, the air is going to fall out of the bottom of this door because it is heavier it is the heaviest portion. So the colder the air is, the heavier it is, it's going to fall out the bottom. As it falls out the bottom, that is going to induce then an airflow into the top, or in through the top of this opening. So when you look at this opening without the air curtain, what you're going to see is air coming out the bottom, going in the top. As it goes in the top, it's going to carry moisture with it. So by applying an air curtain, we can apply enough pressure to overcome the differential of that air difference between the cold and the cool and its weight difference. So yes, the air curtain will do some good. However, what we really have to look at is the vapor pressure differential. The vapor pressure differential is too high for this air curtain to stop it from moving. So if we have a curtain of air, we're moving it across some opening. That curtain is usually 2 inches thick or something like that. At a velocity of 3,000–4,000 feet per minute, we can get some sort of a differential. It's significant, but not significant enough to overcome vapor pressure. So let's first understand vapor pressure. How big, how significant is this pressure that we're dealing with? Vapor pressure being that partial pressure, that part of the pressure of the moisture, of the water vapor in the gas, in the air that is present. So what is that vapor pressure? Vapor pressure is the motive, it is the force that's going to drive that water vapor right through even walls, if they're permeable, from high to low. So how high is it, or how low is it in the areas that we're talking about? Our example today is taken from Atlanta, where our ambient condition outside the building has a vapor pressure of 0.876 inches. That's, I believe, a 74-degree dew point that is outside the building. And then this cooler, in this case, or excuse me, I guess it's a freezer, 10 degrees Fahrenheit, 10-degree dew point, has then a vapor pressure of about 0.07. So from roughly 0.9 to, call it 0.1, whatever, you can round it. What is that? Well, remember, vapor pressure is measured in inches of mercury, So to get it into something that you understand, especially when you're talking about air curtains and fan systems and velocities, we want to change it into water column, inches of water column. So in this case, we have 11 inches of water column differential. That's huge. That moisture is going to want to run from the outside right into your cooler or freezer. Now you may have an a loading dock, and that's a loading dock, believe it or not, on the right hand side there, and that loading dock might be at a condition that's, half of the moisture as outside air. But even so, we're still talking about 5 inches or 6 inches water column vapor pressure differential. It's still a very significant pressure, well in excess of what an air curtain can stop. So our example, how would we look at it today? In Atlanta, that summer ambient design condition, 82 degrees, 74-degree dew point. We've got a 10-degree freezer. Throw that up on your psychometric chart. It is a vapor pressure question. And so we would plot our condition at the cooler, come across here and see it is about the 0.0683 inches of water column. The outdoor ambient condition, bring it across 0.876 inches. That differential, again, very, very significant. So if you need a visual way to communicate this to your clients, to communicate to your staff, we would recommend the use of the psychometric chart to really try to understand that. So the air curtain, again, what is it doing? It's producing a stream of air at a very high velocity, 2,000, 3,000, 4,000 feet per minute, something like that, fairly narrow. It's going to create a pressure that is going to resist and can resist the CFM moving from in and out of the freezer, but it is not going to stop the vapor pressure differential. Vapor pressure is just too high. Air curtains are not going to do it. You're still going to be producing a lot of moisture. So if we can't do it with a strip curtain, if we can't do it with a cooling coil, what can we do it with? And really what it gets down to is desiccant dehumidification. Yes, you can do some moisture removal, some dehumidification with a cooling coil, but you're again going to be limited to that 35 or 45 degree without getting back into trouble with ice and so on and so forth. So we will use desiccants. They regularly operate at or below a 0 degree dew point. You can definitely get that dry if you wish. What then is the solution? Well, first step of the solution, we're going to be looking for the very highest return on investment possible, the highest return on investment. And what is it? Well, the highest return on investment is not product from us. The highest ROI is whatever we would spend on minimizing that moisture. Let's stop it. Let's get it out of the system, stop it before it even gets there. If your client shows themselves willing to invest time, money, and get this, procedural changes, if they're willing to train and teach and document to make a procedural change to minimize this moisture load, they are really showing a commitment to solve the problem. Where do we look first on a cold storage loading dock? The first place we look is the actual doors. To inspect, replace those door seals. The door seals should be in great condition. Here's a procedural change. Let's make sure that that dock door is opened after the truck has completely sealed against the door. In some cases, maybe an airlock needs to be considered. Any weather stripping that's on door sweeps, all the doors. And check this out. If you can see daylight, seal it. As you walk around in this space, any building envelope penetration, duct penetrations, electrical conduits, all those things. You might be in a 10,000 square foot space and you say, well, what's that little bitty 6-inch hole doing? You can be in a 10,000 square foot space and you see a little bitty 6-inch hole up here where this pipe goes in. How much effect can that have? It can be dramatic when you've got an 11-inch vapor pressure out here and 1 inch on the inside. The water is going to push in just like a hose. So number one, what can we do with the building envelope? What can we do with the doors? Let's stop that moisture. Let's move now on the inside, and we'd like to speak to specifically the packaging that happens. So any hygroscopic packagings, wooden pallets, cardboard boxes, all of those things, they are going to bring moisture in them. If you've got them stored in some sort of a warehouse that is unconditioned, they are going to reach a moisture equilibrium. So as you're in a high humidity situation, that is going to pick up moisture. This is supposed to be a scale over here. And you can see what we're trying to demonstrate is as that moisture comes into that packaging material, it is going to become heavier. It's going to be laden with moisture. So the higher the ambient humidity, the higher the moisture content. Now you take that packaging material, and then you put it into the low humidity area, whether that's the loading dock or the freezer itself. Now these things are going to give up that vapor back to the room until it reaches a new equilibrium. And so if, say, 5% of the total weight of the shipped product is the packaging, and that 5% is going to take on 10 or 15% moisture as it moves, that becomes 1 or 2% additional moisture that we can just get rid of it by changing our types of packaging. What can we do that's not wood, that's not cellulose, something like that, these items that are going to take on a lot of moisture. So what can be done to reduce that moisture load? So transfer that from wooden to plastic pallets if at all possible. and if not, stage those hygroscopic packaging materials, stage them in some place that has a lower moisture content. Maybe it's the loading dock itself where we're going to hold a lower condition before it goes into the freezer. Keep the water out of the freezer, if at all possible. So we've been talking about reducing moisture before it gets there. What happens now that we've done all we can do? The moisture is present. What are we going to do? What is the solution? Well, we want to reduce or eliminate ice accumulation below or to the level of dew point. So we must lower that dew point condition of the air to be below that of the surfaces in the space, whether it's the evaporator, the frame, the ceiling, whatever it is in that space. How do we get that much moisture out of it? How much is practically possible? With the desiccant product, and we're just showing a condition here starting in a kind of a cooler, wet condition, which would be similar to what you're seeing on the loading dock. As that goes through the desiccant unit, rule of thumb, we're getting a 30 to 40 grain depression. And so as we go through the desiccant unit, we can get down here very easily to about 5 grains. Now, 5 grains is a 0 degree dew point. It is not a minus 30, minus 40. So if you have a freezer minus 30, minus 40, we are not going to promote getting all the way there with the desiccant, because it becomes very expensive to do so once you get below around this 5 grain level. So in those applications where we're talking about freezers, we're talking about desiccant becoming a 90% solution, 95% solution. You're going to ask Dr. Dry, how do you know it's a 95% solution? Well, if right now you're operating at this zone up here in this level of moisture, and with the desiccant we can get you to this zone. If we're down to, say, 5 grains, if I take 5 and I divide it back into, let's say for easy math, 50, that tells me that it's a 90% solution. So if before that freezer was seeing all 50 of those grains, now it's seeing 5 of those grains. Remember, grains is a measurement of weight. It is weight per pound of dry air. So by taking 45 of those out of there, 45 of the 50, we're solving 90% of the problem in a freezer, minus 30, minus 40. If it is a cooler, then we're talking about, essentially a 100% solution. So we are going to remove moisture by using the desiccant to a significant area. How do we apply that desiccant dehumidifier to those areas? Well, most often the basic unit is going to be in a closed loop or 100% recirculation. Generally speaking, we're not bringing any outside air into that for pressurization or whatever you might be looking for there. It can be done, but not normal. It is not normal to have a post-cooling coil. Why? Because, and here's a point we'll come back to several times now, we are going to put the latent load on the desiccant unit. All the water work that was done by those space evaporators is going to move to the desiccant. And in doing so, it is going to free up, if you will, the sensible capacity then to take on any heat that this desiccant dehumidifier may be providing to the space. So normally there is no post-cooling required. Now, if this is new construction and you want to eliminate the extra equipment of having evaporators in the loading dock, then yes, we would use post-cooling. Now, the way we're going to do this is the return air to our system. We want to draw that air from as near as possible where the moisture comes in. Where is the moisture coming in? It's that most used loading dock door or doors. So we want the return air drawn from near it, and we'll talk about that more in a second, that word near, and then we're going to supply that dry air at the freezer or the cooler door. The idea is that we want to pick up the moisture before it infiltrates, before it comes deeper into the space, before it gets into the cooler or freezer. Why let it be a problem? Let's catch it at the source as near as possible. And then deliver the driest air possible where we need it, which is at that freezer or cooler entrance. What you have before you right now is a plan view of a freezer warehouse. You can kind of see the cut lines here. It was a substantial warehouse, 100,000 square feet or something of that nature. But you can see in this case we had loading docks, ins and outs on both sides. And the exterior doors, looks like there's about 3 of them there. Interior doors into the space, 2. I look at the other side, there's several doors. Looks like there were 30 doors on this side. And then on the doors into the space, fewer. Very common way of doing that. All right, and so the desiccant dehumidifier was placed up on the roof. It can be indoor, doesn't matter. And what we're doing, you can see a little bit here, I'll show you on the next slide, but we're taking the return air into the unit and then supplying it to those other doors. So here is a cross-section view. Here is our deluxe food delivery service, picking up product from your cold storage facility. Remember, as it backs up to the door, we want to make this seal. As they open the door to the delivery truck, there may be some moisture that even comes in from the truck. This return air duct, we want to keep that near the opening, not at the opening. If we keep it at the opening, we can actually induce a flow of outside air or draw on via negative pressure velocity into that duct. So we want to use a lower velocity, keep it a couple of feet away from the door, and then draw that return air up into the desiccant unit where we're going to filter that air. MERV 8 is the only filtration that's required from our standpoint to keep the desiccant wheel clean. If you want better filtration for one reason or another, it sure can happen, but MERV 8s are all we need in terms of servicing the desiccant product and keeping that wheel clean. The air then goes through the desiccant wheel. It's going to come out the other side warmer, but very, very dry. So 84 degrees, but very dry. 2-degree dew point in this case. So then supply that air near the freezer or cold storage opening door. Again, if you supply it too close, then we're going to induce a flow into that room. That's not what we're trying to do. What we're attempting to do is get a dry air pillow right here. A dry air pillow. So as moisture would come in from the loading docks or your processing area, wherever that moisture is coming from, remember, vapor pressure is going to push it there. Whatever your pressurization strategy is, that moisture is still going to move there. It's going to try to get to this cold storage area because the vapor pressure is so low. It's going to want to run there. So if we have this dry air pillow on its way, we're going to catch that moisture before it becomes a problem. We're going to, again, supply that air at the warm side of the cold store door opening with some sort of a simple air distribution. You can call it an air curtain if you will. This one just had multiple T's, worked it very well. Low velocity across that opening. So some sort of distribution. If you do that, this is what's going to happen. On the left you see an application before we provided a desiccant unit. Frost and ice buildup, the conveyor weren't working well, just all these openings, a bunch of ice. Afterwards, frost free. Conveyors were rolling well, openings were free of ice. Here's another room. Check this one out. Does that look like your freezer? Stalactites and stalagmites and all kinds of ice hanging around. Well, after 15 days of a CDI unit, it even exposed, look at this, look at the damage that happened to this electrical conduit up here, just totally ripped up from that ice that had been building up and defrosting over the years. So now, with the add of the desiccant unit, that room is dry. That is the cold storage loading dock application. We want to catch the moisture before it gets to the freezer or the cold storage area. We're going to proceed now and speak about spiral freezers. Again, we want to start with minimizing the moisture load. A lot of that load comes in with the product. So can we do something with an air knife or something to get some of that moisture off before it comes in? Obviously, infiltration through the doors or conveyor openings, whatever it might be, can we reduce the size of those? Can we close them off in some fashion? And if so, that's going to help. This spiral freezer, a rather unique creature, if you will. It has product that is usually entering from the low position as it comes in to it. As it does come in, that conveyor is going to induce a flow, which then includes moisture coming in with that flow. As we go through the spiral, we usually leave high into the packaging area or something like that. So the product flow is that direction. That product has moisture in it. We're going to talk about that a little bit more. But if this is a spiral freezer, then we're going to be freezing the product. How long does it take it to skin, or how long does it take so that the exterior is not giving up the moisture readily? Once it's frozen, now we're going to have to ask it to sublimate that moisture as compared to evaporate, if I can use those terms. So airflow, what's happening with airflow? Well, this is going the other direction, really. Remember this spiral freezer, let's say in our application today, -30. That air is very cold, it is very heavy. Because it's heavy, it's going to fall out of the freezer. So we've got cold air coming this direction. We've measured up to 500 feet per minute, a very significant amount of air coming out of the freezer. And then conversely, then on this end, because it's falling out, we've got 500 feet per minute coming in. So warm air coming in the top, cold air falling out the bottom of our freezer. So that's the airflow. Now let's talk about vapor pressure. This is going to go against even that airflow. So if our processing space, this is entering at the bottom of the spiral freezer, let's say that space is 70 degrees and 80% relative humidity. That's about 0.6 inches of mercury. The freezer on the inside, 0.007. And so that ends up to be about 8 inches of water column differential. Again, vapor going to move right into the freezer even though the airflow is moving out. It moves against airflow right into the freezer. The other end, the airflow is moving in, so it's already coming that way. It is, in this case, a 55-degree room, so it does have a little bit lower, or significantly lower vapor pressure, but still 5 inches of water column pressure differential on that vapor, trying to push it into the freezer. What is our solution? Again, just like the cold storage loading dock, we want to stop that moisture. Stop the moisture before it enters. Don't let it get in there. We want to supply the driest air possible at the inlet of the freezer, not in the freezer. We don't want to create more sublimation. We don't want to dry out the product. They froze that product. The moisture is in the product. They want to keep it there. All right, so we don't want to put that air in the freezer. We want it to catch the moisture before it gets to the freezer. We do that by using a 3-foot to approximately 5-foot long plenum. So right here on the inlet, another one on the outlet. But that is a plenum, stainless steel, 3-sided, cleanable. And then we are going to take air from the dry climate product, the stainless steel unit we talked about earlier, and we are going to provide that air into this plenum at a low velocity, at a distributed velocity, so that we are providing a dry air pillow, again, if I can use that name. As that driest air is right there at the opening without a bottom on this plenum, that air spills out, if you will, around this area. So we end up with a dry air zone right around that opening, with the driest part being right at the entrance of the freezer where we want it. Same thing on the other side. You can use one unit ducted to two locations. You can use two smaller units. Several different solutions to do that. In some cases where you have multiple spiral freezers lined up and there is a interstitial space, loading zone, whatever you'd like to call it, we can dry out the whole area, but that's not normal. Normally these spiral freezers, spiral devices are just right out in the middle of the production area, and you can't dry the whole area. It's just not possible. But let's catch the moisture just as it goes into the room. Now again, this is not a 100% solution in a freezer. Again, so if we start up here, and this is where our condition is in the processing space, 70 degrees, 80% relative humidity, something like that. On the packaging side of the freezer, it's maybe in this zone, and we're taking that air, we're going to dry it out, we're going to bring it down to, like I said, approximately 5 grains of moisture. We're going to provide that air at the opening. So this differential, again, maybe 5 grains to 0 grains, it's a very significant reduction. So what does that mean? So right now, if you're defrosting every 8 hours, let's say you can get through a whole shift without having to defrost that freezer. That's going to move to something like once a week. Okay, so defrost cycles can be changed significantly. Not 100% solution, but enough that you can do a lot more production, that you can get rid of all of these problems. So these benefits, again, we talked about the negatives at the beginning, so now we've got the opposite. We can improve the worker safety, their comfort. We can reduce that ice, that water, those drips. That's going to reduce those occupational injuries. It's more comfortable to work in a lower humidity environment. There's fewer sick days. If we can get rid of that fog, our forklifts can find their way through openings without running into things. We're also going to reduce that energy consumption. Again, by defrost, we can do significant reduction in defrost from 4 a day to 1 a day or something like that. Or you can think of it this way. Instead of having your summer defrost cycles, now you're going to have a winter defrost cycle. So you can get into, again, a significantly longer time between defrosts. And as we do that, the heat transfer on the freezing coils is going to get better. That latent load that we have now moved to the desiccant unit, we're going to use natural gas to do the work. So it's going to move from electrical and your ammonia system to natural gas. Much more cost effective to do it that way. Reducing maintenance costs. We can get rid of the ice chippers. We can improve door operations. Doors sticking or not working at all. Cracked and heaved floors where that moisture gets down into the subterranean levels. Improved product quality, less buildup of ice on the packaging and so on. Improved sanitation, quicker recovery if you've got washdown happening in the area next to this. Improved productivity. We're going to offer flexible product staging by maintaining temperature specifications with those pallets while they're being prepared for shipment. Less downtime, fewer defrosts, talked about that. Improved, if you can believe this, even the electric forklift batteries are going to last longer in this drier atmosphere. One of the large benefits of adding desiccant to your system is you now have 2 tools in your toolbox to do the work. By adding the desiccant, you are going to have independent temperature and humidity control. The desiccant is taking care of the moisture. The cooling coil then can focus on the temperature control. What does that mean? Well, that can allow you to do setbacks now and disassociate the two. So if there's times when higher moisture levels are appropriate, night setback or something, you can start to deal with that. Again, we're going to shift the latent load to the desiccant. That's going to free up then sensible capacity. You can find more capacity than you had before by freeing up those evaporators. There are some other energy conservation techniques we can apply, like reactivation air heat recovery. This is a desiccant unit. We're actively adding energy to the desiccant reactivation airstream. We can recover some of that because this application has considerable run hours. You're looking at something that's running, 365 days a year, 24 hours a day, if you will. That makes a much quicker payback in elapsed days for some sort of heat recovery. So that should be considered. And we talked a little bit about this, but some sort of a occupancy sensor. Is there something that we can do to think about some sort of setbacks, if you will? Now, one of the things that we can offer, that CDI offers, we manufacture a mobile or rental product. We have a number of our customers that would love to employ one of these at your facility as a proof of concept. Is this something that we're wanting to spend capital dollars on? You can pick your worst freezer at the worst time of the year and give it a try with one of these mobile units. So consider employing a proof of concept unit. Again, thank you so much for joining us. This is Tom Peterson from Climate by Design International. We are your manufacturer for desiccant-based dehumidification equipment, along with air handlers for critical process environments. So greetings and salutations from sunny southern Minnesota. Hope you're enjoying the day, and we look forward to seeing you at another webinar or out in the field. Thank you.